And chapter 2 we'll be looking at elements, compound, and mixture. Okay, the first one, the first atomic structure actually. So this chapter 2 will be looking at atoms, elements, and compound. And in this atom, element, and compound, we'll be looking at the atomic structure and the periodic table briefly. And here, the first part we're looking at is elements, compound, and mixtures. First of all substances around us can be classified to either being an element or being a compound or being a mixture. So everything in chemistry around us, chemistry is the study of matter. Chemistry is the study of matter. Physics is chemistry of matter and energy. Chemistry is only the study of matter. So everything in matter can be classified as being an element or being a compound or being a mixture. Okay, compounds are elements that are chemically combined together or that are bonded together. An element is a substance that can take part in a chemical reaction. An element is a substance which can take part in chemical reaction. They are actually atoms. Okay, then mixture are things that are physically combined together, not chemical combination. Okay, now what is an element? We start with the first one, an element. An element is a substance that is made up of atoms that contains the same number of protons. Every atom you mention, which is element, let's say for example you say sodium, the number of protons, whether it's in different isotopy, the number of protons will be the same for sodium. Whether, for example, if you say carbon 6, carbon 12, carbon 13, and carbon 14, they will have the same number of protons no matter what. So when you call something an element is an atom that contains the same number of protons at every point in time, and cannot be split into anything simpler than that. In the real context of it, cannot be split into something smaller than that. So which means an element is the smallest part of a substance which can take part in chemical reaction. An element is the smallest particle of a substance, is the smallest particle of anything which can take part in chemical reaction. Okay, so there are about 180 elements found in the periodic table. About 180. Not all of them are naturally found on Earth. Some are manufactured in the laboratory. Now, what's a compound? Now we know an element, we say, is the smallest unit of a substance that can take part in chemical reaction. Now, what's a compound? So, compound is like a bigger form of elements, like element or atoms of sodium can react with atoms of chlorine to form something bigger. Okay, can combine together to form maybe something like sodium chloride. So, such is a compound. Like hydrogen can react with oxygen to form water, which is a compound. So a compound is a pure substance that's made up of two or more elements chemically combined together. In compound, things don't combine together physically. They combine chemically. For example, if you take sodium plus chlorine, you say sodium plus chlorine, react them together, then you get something different, right? You say sodium, we write the symbol. You say sodium is Na. Sodium is Na, right? Or a little English. Sodium is Na. Okay, this is the symbol of sodium. React with chlorine. The symbol of chlorine is Cl. So if you react with chlorine, you get sodium chloride. Now this sodium chloride is the compound. This sodium chloride is the compound. You get a sodium chloride, which is a compound. Now this, we bond together chemically, okay? We combine chemically. Chlorine and sodium, we join together chemically, right? They will combine chemically. They will chemically combine, not physical. It's not physical. So for that reason, we say a compound. A compound is a substance that chemically combined together, that involves two or more elements. Could be more than two, joining together chemically to form a compound. Now we say there is an unlimited number of compounds because so many different atoms of elements can react together, can combine chemically to form different types of compounds. Compounds cannot be separated into elements by any physical means. Since they cannot combine by physical means, similarly since they cannot combine by physical means, it only takes chemical process for compound to be formed from element. So also when you break the compound down, you cannot break them with a physical means. You need a chemical process to also split them, like thermal decomposition can be one of the ways to split the compound into elements, constituent elements. Now let's take a look at an example of compound. Like sodium chloride we wrote just now, copper 2 sulfate, CuSO4, copper 2 sulfate, calcium carbonate, which is a limestone, calcium carbonate, these are compound. Carbon dioxide is a compound, water H2O is a compound, sodium chloride, salt, table salt is a compound. So things that chemically combine together, they are called compound. Now we move on to mixture. Now a mixture is a combination of 2 or more substances. It could be 2 or more elements, okay, that are not chemically combined together. 2 things or more things that join together physically, they don't mix chemically, okay. Now mixtures can be separated by physical method because you join them together by physical method, so it can also be separated by physical method. A good example is like evaporation, filtration. You know, you can filter things by separating them, right? Separation method. You can filter things because you obviously okay. So we say for mixture, the mixture can be separated by physical method. Why are we able to separate mixture by physical method? Because we can join them by physical method. So one of the physical methods of separating mixture is filtration, evaporation. Okay, when it is joined in a physical way, you can separate them by even boiling. Okay, sand and water. If you join sand and water, you can just filter the water that mix with the sand. You can filter it with use a filter paper and a filter funnel. Oil and water, you can separate them, probably by distillation. Sulfur powder and iron you can separate them. So all these are mixture. Iron and powder and sulfur powder, they cannot be chemically combined together. So if you want to separate them, you can also separate them by physical method. Now let's take a look at this diagram. This is an atom. Atom is just one. When you have 2 atoms combined together, it becomes a molecule. 1 molecule of this atom, this particular atom. But now when you have these same 2 atoms of this, plus another element entirely, different color shows a different element or a different atoms. So when a different atom combined with another 2 or more atoms, it becomes a compound. So this is a compound. Why? Because the elements are not the same. This one, 2 of this one is not a compound, it's just called a molecule. Like you write H2O, if you write H2, hydrogen atom, there are 2 atoms of hydrogen. This is not a compound. This is just 2 atoms of hydrogen. For example, if one atom of hydrogen is just a circle, another atom of hydrogen is just also a circle, another atom of hydrogen is also a circle. For example, okay, let's assume they are same, okay? The thickness, everything, they are just same. Don't mind my drawing, okay? Okay, let's say these are 2 atoms of hydrogen. This is not a compound. This is not a compound. Okay, even if they come together, they touch each other because when they combine together, they become H2 like this. This is a molecule. This is a molecule because it's the same thing. But if you bring something different, like H2O, let's say something different, third one. This third one is different. For example, okay, this third one, let's use a different color. So this third one, let's say there's oxygen. We bring oxygen here. Okay. This becomes a compound. This becomes a compound. This one is a compound. This one is a compound. Because we have one hydrogen here, another hydrogen atom here. One atom is same like an element. Is okay? Atom is like saying you are saying the element. This is oxygen. This becomes a compound because two or more elements are chemically combined together to form this compound. But these 2 are molecules. If they touch it, they are molecules. If you just have one hydrogen atom, it's just an element. If you have one hydrogen atom, this is just an element. Is that okay? So we move on quickly. So if you take a look at this, you have a molecular compound here. Why is there molecules? There are 2 that are same. Right? This and this are same, so it's a molecule. Then different color, different color. So this is a compound. Molecule and a compound is found here. Here, molecule is found only here. Molecule and a compound is also found here. You can see these two that have the same color is a molecule, and this different color makes it a compound. So you have a molecule and compound here, molecule and compound, molecule and compound. So you can simply say compound anyway. Compound, compound. Then these ones are not, these are mixture. You just take different things, you just put them together. Okay, this is a mixture. This is not a compound. You see, because you know why? Because these ones are separate. They are all separate. Okay. Now, with this, we go to the next one, the next section of today's class. We go to the next section. Now that we understand element, compound, and mixture, we go to the next one. So the next one, before we go to the next one, we're going to look at the atomic structure. Before we do that, let's listen to this our tutorial.
In this video, we're going to look at the structure of an atom and subatomic particles. Everything is made of atoms, but what are atoms made of? You've probably been using the word particles for atoms. An atom is the smallest single particle. It contains a central nucleus that is surrounded by electrons, which are one type of subatomic particle. Electrons are arranged in shells, although you may sometimes hear them called orbits or orbitals because of how they move around the nucleus. In diagrams, electrons are commonly shown as dots or crosses. The nucleus contains two different subatomic particles, the neutrons and protons. Overall, an atom contains three different subatomic particles, the protons, the neutrons, and the electrons. So when we talk about the mass of an atom, we're mainly talking about the nucleus. This is because the nucleus contains almost all of an atom's mass. Protons and neutrons both have a relative mass of 1. By comparison, electrons have almost no mass. In an exam, you do not need to know the exact mass of an electron, as it's not in the specification. This means that saying its mass is almost nothing, negligible, or 0 will be enough for the mark. Next, we need to consider the relative charges of the subatomic particles. Protons are positive. They have a +1 charge. Neutrons are neutral, which means they have 0 charge. Here are two little tricks to help you remember these charges. The letter P. P for positive, P for proton. The word neut. Not N-E-W-T like the animal, but N-E-U-T. Neut for neutral, neut for neutron. Overall, atoms are not charged, which means that for every positive proton, there must be a negative electron. There is no trick for this one, you just need to remember that electrons are negative with a -1 charge. Atoms are made up of three different subatomic particles, the proton, the neutron, and the electron. Protons and neutrons are found at the centre of an atom, which is called the nucleus. Electrons orbit the nucleus in shells. The mass of both protons and neutrons is 1, while electrons have almost no mass. Protons have a positive charge, +1. Neutrons have no charge, 0. Electrons have a negative charge, -1. Don't forget to check out our other fantastic resources here at Save My Exams.
Okay, so we've seen a little bit tutorial of the atomic structure. With this, we have an idea before from lower science grades. So we already know that all substances, they're made up of tiny particles, the kinetic theory of matter. So all substances are made up of tiny particles of matter called the atoms. The tiny particles of matter is called the atoms, and which are the building block of all the matter in chemistry. So the atom is the foundation, is the unit, like you say cell in case of biology. Cell is the unit building blocks of life, and atoms is the building block of any chemical or every matter in chemistry. Now every atom, or each atom, is made up of subatomic particles. There are 3 subatomic particles: the proton, the neutrons, and the electrons. There are 3 subatomic particles we need to get familiarized with. They are the protons, the neutrons, and the electrons, right? The protons and the neutrons, they're found inside the nucleus of the atom. Every atom has a nucleus, and that's the densely populated area of the atom. That's where we have the mass of the atom found mostly. The electrons are scattered around. They orbit in shell. They orbit around the nucleus. So the nucleus contains what? The nucleus of an atom, just like you have a nucleus in biology, the nucleus of a cell. Atom also has a nucleus. The nucleus of atom contains 2 things: the protons and the neutrons. The protons and the neutrons, they are found in the nucleus of the atom. And while the electron, the 3rd subatomic particle, the electron, they revolve around the nucleus of the atom. They revolve around the nucleus in shell. They orbit around it. You can say they orbit around it, or they move in shell. Is that okay? So that's for each of them. Now we say the protons and neutrons, they're found in the center, in the nucleus, the place called the nucleus. The electrons, they move very fast around the nucleus, and they orbit around it in shell. Is that okay? Now we say the mass of the electron is almost negligible. It's very small, 1 over 1,840, or 1 over 1,850, or precisely 1 over 2,000. Okay, precisely 1 over 2,000. The mass of electron is very small. It's very negligible. Okay, so that's why we say the mass of the whole atom is mostly what is inside the nucleus. Okay, because the mass of this one is negligible. It's like close to 0. Okay, it's nothing meaningful. But the mass of the proton and the neutrons, they add up to the mass of the atom. Is that okay? Now let's move on quickly. Let's see the second tutorial and see how we take it up from there.
In this video, we're going to be looking at the atomic number, mass number, and how we can use these to calculate the number of protons, neutrons, and electrons in atoms and ions. A chemical symbol, as seen on the periodic table, gives detailed information about the element. The actual chemical symbol gives the name of the element. In this case, the letter X is used to represent a general element. If the letter X was replaced with a H, we would be looking at hydrogen. The letter Z represents the atomic number of the element. Exam boards are adopting the International Union of Pure and Applied Chemistry Convention, which means that the atomic number should be the top number on a chemical symbol. You might see the atomic number at the bottom in older textbooks, revision guides, and resources. Remember, the atomic number is always the smallest number. Periodic tables should also have a key that you can use to check which number is the atomic number. The letter A represents the mass number of the element. This gives the number of protons and neutrons in the nucleus of an element. Electrons do not contribute to the mass number because they have a negligible mass. The chemical symbol for lithium has an atomic number of 3, which means that there are 3 protons. There is no charge on lithium, which means there are also 3 electrons. The mass number of lithium is 7, so the number of neutrons is 7 minus 3, which equals 4. Be careful. Sometimes an exam might give you a specific order of subatomic particles for you to answer with. This example contains the same information, but the order of the subatomic particles has changed. Make sure that you check which subatomic particle you are writing the answer for, because it can be an easy but frustrating mark to lose. To help answer this question, remember the number of protons is the atomic or top number. So boron has 5 protons, the sodium ion has 11 protons, and the fluoride ion has 9 protons. Elements have no overall charge, which means that boron has 5 negative electrons to cancel out the 5 positive protons. For the number of electrons in an ion, you also have to consider the charge. A sodium atom would have 11 electrons, but it is a sodium ion with a single positive charge, which means that it has lost an electron. Therefore, the sodium ion has 10 electrons. The fluorine atom would have 9 electrons, but it is a fluoride ion with a single negative charge, which means that it has gained 1 electron. Therefore, the fluoride ion has 10 electrons. To calculate the number of neutrons, you subtract the atomic number from the mass number. For boron, 11 minus 5 equals 6 neutrons. We've now scored 1 mark for the correct number of protons, neutrons and electrons in boron. For the sodium ion, 23 minus 11 equals 12 neutrons. We've now scored the 2nd mark. For the fluoride ion, 19 minus 9 equals 10 neutrons. We've now scored the final mark. The information here tells us that there are 7 protons, which means the atomic or top number is 7. If we look this up on the periodic table, we can see that the element is nitrogen. There are 7 negative electrons that cancel out the 7 positive protons. So this is an element, not an ion, which means there is no charge. The nucleus contains protons and neutrons, which means that the mass of the element is 7 plus 7. Therefore, the mass number is 14. We now have the complete chemical symbol for this question. For this question, we will work 1 row at a time. The number of protons gives the atomic number. Therefore, the first row has an atomic number of 4. Looking this up on the periodic table gives us the chemical symbol Be for beryllium. The mass number is 4 plus 6, which is 10. Since the number of protons equals the number of electrons, there is no charge. Overall, this gives 410 beryllium for the first mark. Be careful, as the mass number for an element on the periodic table is typically not the correct answer. The second row has an atomic number of 1. Looking this up on the periodic table gives the chemical symbol H for hydrogen. The mass number is 1 plus 1, which is 2. Since the number of protons is not equal to the number of electrons, there is a charge. 1 electron has been lost, which leaves a positive 1 plus ion. Overall, this gives 1, 2 hydrogen as a 1 plus ion for the second mark. The third row has an atomic number of 8, which from the periodic table is O for oxygen. The mass number is 8 plus 8, which is 16. The number of protons is not equal to the number of electrons. There is a charge. 2 electrons have been gained, which cause a 2 minus ion. Overall, this gives 816 oxygen as a 2 minus ion, the final mark. The atomic number tells you the number of protons. The number of electrons is equal to the number of protons, but this is only for elements. For a positive ion, the number of electrons is less than the number of protons. For negative ions, the number of electrons is more than the number of protons. The number of neutrons is calculated by doing mass number minus atomic number. You should be able to use a chemical symbol to determine the number of protons, neutrons, and electrons for any element or ion. Don't forget to check out our other fantastic resources.
Okay. So we move on. We've seen the calculation, how it's been done. First of all, we see the size of atom. We say it's so tiny that we can't really compare the masses in the conventional unit, like in kilogram or gram. They're so small. We don't use gram or kilogram for the unit, so we just use the relative atomic mass in this regard. Okay, we say 1 relative atomic mass is equals to 1 over 12 of the mass of carbon 12. Is equal to 1 over 12 of the mass of carbon 12. So because the masses are very small. So for proton, a relative mass is 1, and the charge is 1 plus 1. Neutron, the mass is also 1, but it has no charge. So charge is neutron, is 0. An electron, the mass is 1 over 1,840, like I told you before. And you can also say 1 over 1,850, or you can say 1 over 2,000. It's okay, whichever you say this is okay. and the charge of electron is -1. Is that okay? The charge of electron is -1. Now let's go to defining proton. What's a proton number? The proton number is called the atomic number. The atomic number is the proton number is the number of protons that is in the nucleus of the atom. The number of protons that you see inside the nucleus of the atom is the atomic number, is also the proton number. Now the symbol is usually Z. Okay, in chemistry we use Z for the symbol for proton or atomic number, and it also has the number of electrons present in the neutral atom. For every neutral atom, the number of protons equal to the number of electrons, except the substance has a charge. If it has a charge, then the number of protons is no longer the number of electrons. But if it's neutral, meaning there's no positive charge or negative charge, the number of protons equal to the number of electrons. Is that okay? Now let's go to defining the mass number. Mass number is the sum. It's also called the nucleon number, and is represented by letter A, capital letter A. The symbol is capital letter A, and it's the number of protons and the number of neutrons that are found in the nucleus. It's just the content of the nucleus, what is found in the nucleus. Remember, the proton and the neutrons are found in the nucleus of the atom. So the proton is like adding the number of a proton plus the number of neutrons that are found in the nucleus. Okay, that's what we call the nucleon number or the mass number. Is that okay? It's represented by letter A. Okay, and so since we know that Z is the proton number or atomic number and letter A is the atomic number, then we can simply show this. For example, if we show an element, if we show a symbol for an element, let's say we show a symbol for an element, we say here we write, previously we used to write the mass here, but the AUPAC say it's better, they've adopted in their latest conversion that the mass should be at the bottom. So if you see periodic table, you see the mass is at the bottom and the proton number is at the top, is the one at the top. Previously we were writing the mass on top and the proton number at the bottom. But there's what they call AUPAC, International Union of Pure and Applied Chemistry. AUPAC's conversion, the latest conversion, they all agree that the mass number should be written at the bottom, while the proton number should be on top. Okay. So here, if you want to find the mass number is the number of protons plus the number of neutrons. The mass number or nucleon number is equal to the number of protons or number of the atomic number plus the number of neutrons Okay. So we use this to calculate the mass number or the nucleon number. Is that okay? So let's move up quickly. So you can make anyone the subject of formula depending on what you're looking for. Okay? And you can always check your periodic table to see the mass number, the atomic number of any element. So the mass number is the total number of proton and neutron. This A is the total number of proton and neutron. Then Z is the atomic number. I told you we used to write it up top. So you can either write it up or write it at the bottom. It doesn't matter. Okay, but in the last conversion they say we should be putting A at the bottom and put Z on top. The atomic number, don't worry, don't say, will this not confuse us? No, the bigger one is the mass number. Whether it's written at the bottom or it's written at the top, the bigger number is the mass number. The atomic number is the number of protons or the number of protons in the nucleus. The number of protons in the nucleus, which is represented by Z, is the atomic number. Now this is a chemical symbol for an element. So we use this X to represent a chemical symbol for an element. How to calculate the number of protons, neutrons, and electrons? Number of protons equal to number of electrons if the atom is electrically neutral. If the atom is not losing electron or gaining electron, if it's just an atom, it's not an ion, then the number of protons equal to number of electrons. So you should take this. If an atom is just an atom, let's say for example sodium, if you take sodium, the atomic number, the mass number, it doesn't matter where I write it. If I write the proton number, that's Z on top, and the mass is 23 here, right? Now let's use this one to demonstrate that. What's the number of protons? Number of protons is 11. Number of protons is what? Which is same as atomic number, is 11. Number of protons, which is same as atomic number, is 11. Number of electrons also, always same as proton. If the atom is an atom, it's not an ion. So the electron will also be 11. Okay? And then what if you have to find the neutron? Number of neutrons is equals to mass number, or the nuclear number, mass number, which is represented by A, minus Z, minus the proton number, or what you call the atomic number. Proton number is same as atomic number. So the number of neutrons is equal to the mass number, which is 23, the mass or the nuclear number, which is 23 minus 11. 23 minus 11. So when we subtract this from 11 from 23, we get 12, right? So this is equal to 12. This is equal to 12. So the number of neutron is equal to 12. But both electrons and protons are 11, 11. But this is on one condition. What if we have another condition, like the same sodium is no longer a sodium atom? Okay, you know, if you lose or gain electron, you become an ion. If an atom loses or gain electron, it becomes an ion. If you lose electron, you become positively charged, because there will be more proton. Because if you lose electron, you know they are same. If you lose electron, there will be, if you lose one electron, there is now 11 proton but 10 electron. So you are now more proton than electron. That's why you become plus. Because you know proton is positive. So you are now more proton than electron. That's why you become plus. What if you gain electron? Like in the case of chlorine is 17. So if a proton number is supposed to be 17, electron is supposed to be 17. But if chlorine gain let's say 1 electron from sodium, if chlorine gain 1 electron from sodium, then the electron will no longer be 17. Electron is supposed to be 17, right? But if you gain electron, you know, when you gain electron, you now have more electron than proton, so you become negative. If you gain electron, your number of electrons will now be 18, because you gain chlorine gain 1 electron, for example. So an ion, it is now, when you are an ion, your electron differs now. Here, the number of protons will still remain 11 for sodium. Number of protons will still remain 11. But remember, sodium lost 1 electron. So electron will now be 10. Electron will now be 10 for sodium. Sodium ion will now be 10. In fact, that's why you have positive, because the proton is now more than the electron. That's why you have plus. If the electron is more than the proton, like in the case of chlorine, electron is now more than proton, because you gain 1 electron, you become negative. Because the electron is negatively charged. Become negative. So that's the difference between ion and an atom. That's the difference between ion and an atom. So let's move on quickly. So we've also itemized how to do the calculation. An atom is neutral. An atom is neutral, and therefore it has the same. Electron will have the same number of protons when an atom is electrically neutral. Neutral, we already explained how to do the calculation. You say the mass number or the nuclear number minus the proton number. Okay. Now here is a work example. It says determine the number of protons, electrons, and neutrons in an atom of element X with atomic number 29 and mass number 63. So atom X, 29 here, and atomic number 63. The mass number 63. Atomic number is 29, mass number is 63. So this question wants us to calculate the number of protons. So number of protons will still be 29, because it's the atomic number. Number of protons will be what? 29. Proton will be 29. Because number of protons is the atomic number. Atomic number is equal to the number of protons that are found in the nucleus of the atom. Now, number of electrons will be what? Because they did say this is an ion, right? They did question, except they say it's an ion. If they did say an ion, they determine the number of protons, electrons, and neutrons in an atom. They're talking about atoms of element with atomic number 29 and 63. So it's not an ion. It's not an ion, so it's just an atom. So since it's an atom, number of electrons will also be 29. If it's an atom, number of protons equal to number of electrons. Number of protons equal to number of electrons. But if it's an ion, we know whether it loses or gains electron. Then we're able to tell. Now the number of neutron is the mass number, which is A, minus the atomic number, which is Z. Mass number or nuclear number minus the atomic number or number of protons. So this is 63 minus 29. What do you get? 63 minus 29. What do we get? 63 minus 29. 32, right? 34. Okay, so this gives us 34. 34. So number of neutrons is 34. Okay, your neutron is 34. And your electron is 29, proton is 29. So That's how we do this type. See, number of neutrons 34, and your number of proton and electrons are same. Number of protons 29, and since it's neutral, number of electrons also 29, and this one. So that's for this part. Let's go to the next part quickly. Now for this next part, we're going to look at the electronic structure, what we call the electronic configuration. Let's take a look at the electronic structure. So let's hear from this.
In this video, we're going to be looking at the electronic structure of atoms. An atom is made of a central nucleus containing the protons and neutrons, with the electrons orbiting the nucleus in shells. There is a limit to the number of electrons that a shell can hold. The first shell can hold a maximum of 2 electrons. The second shell can contain up to 8 electrons, and the third shell can also contain up to 8 electrons. When you're drawing diagrams, after 4 electrons, start to pair them up. Electrons always fill the lowest energy shell first, which is the shell closest to the nucleus. There is a clear link between the periodic table and the electrons in a shell. For example, the first period contains 2 elements, and the first shell can hold a maximum of 2 electrons. So, we can see a hydrogen atom with 1 electron, and a helium atom with 2 electrons. Now that the first shell is complete, the second shell starts to fill. The second period of the periodic table contains 8 elements, and the second shell can hold a maximum of 8 electrons. So we can see a lithium atom with 3 electrons, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon with a full outer shell of 8 electrons. Now the second shell is complete, the third shell starts to fill. Again, the third period contains 8 elements, and at this level, the third shell can hold a maximum of 8 electrons. So we can see a sodium atom with 11 electrons, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon with a full outer shell of 8 electrons. For the fourth shell, we only need to apply this model to potassium with 1 outer electron and calcium with 2 outer electrons. Electronic structure tells you how the electrons are arranged in the shells around an atom. You may also hear it called shorthand notation. We will use hydrogen, carbon, and sulfur as examples. Electronic structure is given as a series of digits. The number of digits tells you how many shells there are. For example, hydrogen has 1 shell, so it will have 1 digit. Carbon has 2 shells, which means that it will have 2 digits. And sulfur has 3 shells, which means that it will have 3 digits. The actual digits tell you how many electrons are in each shell. Hydrogen has 1 electron, so it has an electronic structure of 1. Carbon has 2 electrons in the first shell and 4 electrons in the second shell, so it has an electronic structure of 2,4. Sulfur has 2 electrons in the first shell, 8 electrons in the second shell, and 6 electrons in the third or outer shell, so it has an electronic structure of 286. The digits should always add up to the atomic number. In part A, you're being asked about a potassium atom, which has an atomic number of 19. Since it is an atom, the number of protons equals the number of electrons, which means a potassium atom has 19 electrons to place. Remember, each shell can hold a maximum number of electrons. This means that there will be 2 electrons in the first shell, 8 in the second, 8 in the third, and 1 in the fourth shell. An answer of 2881 gains the mark. In part B, you're being asked about a nitrogen atom, which has an atomic number of 7. Again, since it is an atom, the number of protons equals the number of electrons, which means a nitrogen atom has 7 electrons to place. So, there will be 2 electrons in the first shell, which leaves 5 for the outer shell. The correct diagram gains the mark. For both questions, the number of electrons should add up to the atomic number. Horizontal rows of the periodic table are periods, and the vertical columns are groups. Each group is linked to at least one number, which is usually found above the group. For example, Group 1, Group 2, Group 7 or 17, and Group 0 or 18. Some groups have specific names. For example, Group 1 are the alkali metals, Group 2 are the alkali earth metals, Group 7 or 17 are the halogens, and Group 0 or 18 are the noble gases. As you move down the group, the number of shells increases by 1, but elements within the same group have one thing in common. All Group 1 elements have one outer electron. All Group 2 elements have 2 outer electrons. All Group 7 elements have 7 outer electrons. And all Group 0 elements have a full outer shell of electrons. This is what makes them unreactive. Although they can be referred to as Group 17 or 18, this does not mean that the halogens and noble gases have 17 or 18 electrons in their outer shell. Part 1 asked for one similarity and one difference across a period. A period has the same number of electron shells. This gains 1 mark. Since the elements from lithium to neon are in period 2, you could also say that they have one full shell. The number of outer electrons increases by 1 as you move across the elements from lithium to neon, which means they have a different or increasing number of outer electrons. This gains the 2nd mark. The word outer is not necessarily needed for the mark, but you should be putting it in your answer. Part 2 asks for one similarity and one difference down a group. A group has the same number of outer electrons. This gains the 1st mark. Since the elements from beryllium to strontium are in group 2, you could also say that they all have 2 outer electrons. The number of shells increases by 1 as you move down the elements from beryllium to strontium, which means they have a different or increasing number of shells. This gets the 2nd mark. You could also use the phrase energy level to replace the word shell. For this question, there is no need to explain your answer. Electronic structure is a way of writing or drawing how the electrons are arranged in the shell of an atom. The first electron shell can hold up to 2 electrons. The second and third electron shells can hold up to 8 electrons. When it is written, an electronic structure is a series of numbers. The number of digits tells you how many shells there are, while the digits themselves tell you how many electrons are in each shell. If elements are in the same period, they have the same number of shells, but the number of outer electrons increases by 1 as you move from left to right. If elements are in the same group, they have the same number of outer electrons, but the number of shells increases by 1 as you move down the group. Don't forget to check out our other fantastic resources here at Save My Exams.
Okay, so let's move on. We've seen the tutorial regarding the explanation on how we arrange the electrons. Okay, the first share, we're not going to spend time because we're going to the next one. Yeah, the first share, which is the one closest to the nucleus, holds a maximum of 2 electrons because there are 2 elements in group 1 of the periodic table, in the period 1 of the periodic table. So the second one and the third one, they have maximum of 8 electrons. Okay, 2 electrons in the first shell, 8 electrons in the second, and 8 electrons in the third shell. So once we know this, then we're good to go. Now the electronic configuration, which is the one I want to show, is here's the atomic number and the corresponding electronic configuration. So for hydrogen is 1, and the electronic configuration is 1, of course. Helium is 2, and is 2, of course. Then when we get to lithium, the first electronic configuration, you write the first shell will hold 2 electrons, and then if you write 2, remaining only 1. The second shell will hold only 1 electron. If you have beryllium, you have 2, 2. If you have boron, you have 2 and 3 electrons. That means there are 2 shells. First shell will hold 2 electrons, and the second shell will hold 3 electrons. If you have carbon, which is atomic number 6, first shell will hold 2 electrons, and the second shell will hold only 4 electrons. So that continues till you get to neon. In neon, since atomic number is 10, the first shell will hold 2 electrons, and the second shell will hold 8 electrons. Once you get 8, the shell is full. So second shell is full. That's, the maximum number of electrons that can be held in one shell is 8 electrons. So once you reach here, the next one, you must go to third shell, meaning you must have another shell, third one. So for 11, like sodium, atomic number 11, the first shell will hold 2, second shell will complete 8, and the third one will be 1 again. To start again with 1, 2, 3, till you get to 8. So magnesium is 2, 8, 2, because it's atomic number 12. It will continue again. Aluminium will be 2, 8, 3, first shell 2, second shell 8, third shell 3. Silicon is 2, 8, 4, first shell 2, second shell 8, third shell 4, till we get to 8 again, which is argon. All the noble gases, okay, because they are all complete in the outer shell. So we have 2, 8, 8. All these ones, they are not reactive, like neon, helium, neon, and argon. They are not reactive because they complete the outer shell in each of the electron. Okay. Then potassium is the fourth one. Now you have 2, 8, 1, 2, 8, 8, 1, 2, 8, 8, 2 for calcium. We continue like that till this one complete 8 again. Is that okay? So for electron, we either use cross to represent or we use dot to represent electrons. Like this magnesium, the first shell holds 2 electrons. Only 2. It depends. Your arrangement can put one here, put one at the bottom here, or you put them together. Second shell holds 8, 2, 2, 2, 2. That's 8. Third shell only 2 because it's 2, 8 C. For magnesium, it's 2, 8, 2, 2, 8, 2. So you can see from here, if you're showing it in the diagram, 2 electrons in the first shell, 8 electrons in the second shell, and 2 electrons in the third shell. Okay, so that's that for that. If you have chlorine, in the case of chlorine, let's take a look at chlorine. You have 2, 8, because chlorine is 17. The first shell will hold 2, second shell will complete is 8, which is 10, altogether 10, remainder 7. So the third shell will hold 7. So you have the first shell holding 2. You see, we put 1 here, and we put 1 here. I told you the arrangement can be like this. And then the next one you have 2, 2, 2, 2. That's 8. So we now, second shell has 8 now, altogether 10. First and second 10. The third one, 1, 2, 3, 4, 5, 6, and there's 7. So this is how to show it in diagram, and this is how to show them in digits. Is that okay? So this is called electronic configuration. Electronic configuration. Okay, here's a periodic table to help us to know the atomic numbers to see the elements, how they are arranged in period. This is first period in the periodic table. This first period, period 1. Horizontal arrangement is called period. Vertical arrangement is called group. This is group 1, which are called the alkali metals. Group 1s are called the alkali metal. Why? All group 1, they end with 1 electron in the atmosphere, like lithium, end with 1. If you come here, you see lithium, end with 1. Lithium is number 3, atomic number 3. Lithium, end with 1 in the electronic configuration. So it will be in group 1. Anyone that ends with 1 will be in group 1, like sodium ends with 1. Sodium will be in group 1 in the periodic table. Look at this one, potassium ends with 1. So potassium will be in group 1. So if you do the electronic configuration, group 1 will end with 1 electron in the atmosphere. So all these one like lithium, sodium, potassium, rubidium, calcium, and francium, they all end with 1 in their periodic table. They all end with 1. So they'll be in group 1. The one that ends with 2 like beryllium, magnesium, let me show you those 2 only. Beryllium, magnesium, beryllium, look at beryllium. It ends with 2 in the electronic configuration. Magnesium ends with 2 also. So they will be in group 2. Anyone that ends with 2 and this one and calcium, they end with 2. Anyone that ends with 2 will be in the group 2 in the periodic table. Will be in the group 2. So the number of electrons that you have in your atmosphere determine your group. The number of electrons you have in your atmosphere determines your group. And how many shell you have determine your period. If you have 1 shell, you have 1 period. Like this one has 2 shells. 2 and 2, these are 2 shells. The first one is 1 shell, the second one is another shell. This one has 3 shells. So it will be in period 3. Sodium will be in period 3. It has 2, 8, 1. So it has how many? It has 3 shells. This is the first shell, second shell, third shell. So it will be in period 3. The number of, you see, sodium is in period 3. Look at period 1. Period 1 is only hydrogen and helium. This is called period 1. Period 2 is lithium, beryllium, boron, carbon. This is period 2. Period 3 is this one. So the number of shares you have determines your period. The number of shares you have determines your period in the periodic table. Okay, let's go to the next one so we can quickly round up our chapter 3. Okay, I think we're in the last one, the isotope, the last part of this chapter. Let's move quickly. What is an isotope? An isotope of an element is the same element, but it has different mass numbers. It has the same number of protons but different mass number. For example, if we write carbon, just a minute. Okay, if we write carbon 12, let's say we write carbon 12. Permit me to put the mass on top. You know the atomic number is 6, and we also have carbon 13. We have carbon 13. We have carbon 13, and then we have carbon 14. We have carbon 14. So it's one carbon. Atomic number is 6 for all of them. Atomic number is 6. Which number of protons is same, but they have different mass number or nuclear number. Hence, because of that, they have different neutron. Now their neutron will not be same. Proton and electron are same. Their number of protons and electrons are same because the atomic number is 6. But neutron is different for the different. So neutron here will be 12 minus 6. So 12 minus 6 will give us 6 for this carbon 12. So the number of neutron is what? Number of neutron is what? 6. But for this one, let's see the neutron for this one. The number of neutron for this one. The number of neutron for this one, for carbon 13, will be 13 minus 6. 13 minus 6 will give us 7. 13 minus 6 will give us 7. So the number of neutron here is 7, it's not 6. See, the number of neutron here is 7, it's not 6. Okay? So we say this type of element that can exist in different form, but they have the same atomic number and the same number of electrons, but they have different neutron mass numbers which result to different neutron numbers. Such elements are called isotope. They are called what? Isotope. Elements that have the same atomic number but have different mass numbers, they are called isotope. Here will be 14. Here will be 14 minus 6, which gives us a number of neutron 8, which gives us number of neutron for this one to be minus 6. Minus 6, which gives 8. So you can see each of them, the neutron is not the same. Here the neutron is 6. Here the neutron is 7. Here the neutron is 8. So such elements, we call them isotope. Elements that have the same atomic number, but they have different mass number. Hydrogen also have different isotopy. We can just explain hydrogen straight away from here. We have hydrogen with one electron or one proton. Hydrogen, one proton, one mass number. One mass number, the mass number is 1, the proton number is 1. This is called the basic hydrogen that you know. So here, the number of proton is 1, number of electron is 1, because number of proton equal to number of electron if something is not an ion. Number of proton equal to number of electron if something is not an ion. Now, how do you find the neutron? You say the mass minus the proton, right? 1 minus 1, 0. So the number of neutron here is 0. Now let's go to the second hydrogen, which we call deuterium. The second hydrogen is called deuterium. In deuterium, the number of proton is 1 and the mass is 2. So if you want to find the neutron, you say 2 minus 1, you get 1. So proton is 1 here, electron is 1 because proton and electron are same. Proton is 1, electron is 1, and neutron is 1 because 2 minus 1 is 1. So this one, it all has 1, 1, 1. Now we go to tritium. The third hydrogen is called tritium. The third isotope of hydrogen has 3 in their mass. So this is the symbol. The number of proton is 1, which is the atomic number, and the nuclear number or the mass number is 3. So here, the number of proton will be 1, proton will be 1, electron will be 1, because proton and electron are always same if it's an atom. Okay, so proton is 1, electron will be 1. But neutron will be what? Neutron is always the mass minus the proton. So 2 minus 1, you get 2. And 3 minus 1, you get 2. So the neutron is 2 for this case. This type of element, like hydrogen, like carbon, like uranium, that can exist in different nature, even though you are talking about the same element. They have the same number of proton, but different mass number. They are called isotope. They are called isotope. Okay, we're going to look at the properties of isotope. They have the same chemical property since they have the same number of electrons. they have the same, look at all of them, electron is 1. For hydrogen here, electron is 1, deuterium, and for hydrogen, electron is 1. And for tritium, electron is 1. So they have a number of electrons all same. So isotope, they have all same electrons. So you say they have the same chemical property. Electron is responsible for the chemical property of an element. Electron is the reason for the chemical property of an element. So for that reason, you say isotopes are atoms which have the same chemical property but different physical property. They have the same chemical property. One way of saying it, you say isotopes are atoms which have the same chemical property but different physical property. You can say that. Or isotopes are atoms which have the same number of protons but different number of neutrons. Same number of protons but different number of neutrons. Another way to say it, okay, to define an isotope. Now let's move on. The next one is to listen to this tutorial and see how this relates. Also, we'll talk about relative atomic mass.
In this video, we're going to be looking at isotopes and relative atomic mass. Relative atomic mass is often just called mass, but you need to know the specific detail of what it is. It can be found on the periodic table. It should be the bottom number, but it is always the larger number associated with the element. Relative atomic mass is often written as AR. To define relative atomic mass, it helps to work backwards. Mass. This is the average mass. Atomic. In an exam, you might score the mark for saying of an atom, but you should be saying of the isotopes of an element. Relative. The idea of relative means that there is a comparison. This comparison is specifically to 1/12 of the mass of a carbon-12 atom. This is quite commonly missed out or incorrect in people's definitions of relative atomic mass, and therefore costs you a mark. Many elements have different isotopes. For example, any atom of lithium has the same chemical properties because it has 3 electrons, shown as red circles. The difference between isotopes is in the nucleus. We will look at the protons and neutrons in the nucleus of lithium-6 and lithium-7. Both isotopes contain 3 protons, shown as green circles. Lithium-6 has 3 neutrons, while lithium-7 has 4 neutrons. If you're asked to define an isotope, the key marking points are about the number of protons and neutrons. To calculate the relative atomic mass of an element, you essentially do a mean average calculation. For example, 2 stable isotopes of chlorine are chlorine-35 and chlorine-37. If they were in equal quantities, then the relative atomic mass would be 35 plus 37 divided by 2. This would give a relative atomic mass of 36. But the relative atomic mass of chlorine on the periodic table is not 36. This is because there are 3 atoms of chlorine-35 every 1 atom of chlorine-37. This information can be presented in a number of different ways, as a ratio, a written sentence, or a table. It could also be given as a graph of relative abundance. For all of these, you would do the same calculation. Add up the masses of all 3 chlorine-35 atoms and the single chlorine-37 atom. Then divide that number by 4 to get a relative atomic mass of 35.5. The information could also be given as a graph of percentage abundance, which would show 75% chlorine-35 and 25% chlorine-37. For percentage abundance calculations, you multiply the mass of each atom by its percentage. 35 times 75 for chlorine-35 at 75%, and 37 times 25 for chlorine-37, 25%. Then you divide the total by 100, and again get to a relative atomic mass of 35.5. When you're doing these calculations, make sure you divide by the correct number. For relative abundance, divide by the number of isotopes. For percentage abundance, divide by 100. In this question, we're working with percentages. This means that the total percentage abundance of 58A and 60A will be 100. Relative atomic mass calculations are very methodical. First, we need to calculate the abundance of 60A, which will be 100 minus 68.08, giving a value of 31.92%. Then we calculate the relative atomic mass by multiplying each mass by its percentage and then dividing by 100. This working will get you 1 mark. The question asks for your answer to 1 decimal place, so the calculation will give a relative atomic mass 58.6 for the second mark. If you made a mistake in your calculation, you could still potentially get 1 mark if you have shown your working. For part B, you look up your relative atomic mass answer on the periodic table. Make sure you're looking at the mass number, not the atomic number. 58.6 is closest to 59 for nickel or 59 for cobalt. Therefore, either answer is acceptable for the mark. When calculating relative atomic mass, your answer should always be between the highest and lowest values. For this question, your answer must be between 58 and 60. You need to know the definition of relative atomic mass as the average mass of the isotopes of an element compared to 1/12 of the mass of an atom of carbon-12. Isotopes are atoms of the same element that contain the same number of protons but a different number of neutrons. Having the same number of electrons isn't always included in the mark scheme, as this gives the isotopes the same chemical properties. Relative atomic mass is a mean average calculation with information presented as ratios or percentages written in sentences, tables or graphs of relative abundance, which means that you will divide by the total number of isotopes. And finally, tables or graphs of percentage abundance, which means that you will divide by 100. Don't forget to check out our other fantastic resources here at Save My Exams.
So we've seen how to calculate the relative atomic mass, right? So because that's the big important thing here. It's always not just, for example, like chlorine. You have to look at the percentage of abundance of each one. You know, we have chlorine 35, we have chlorine 35, and we have chlorine 37. So if you want to find relative, first of all, you must know how to define relative atomic mass. Relative atomic mass is symbolized as A arrow, substrate arrow. Okay? Relative atomic mass is written like this. It's the average masses of isotope of an element. The average mass of the isotope, because you are describing isotope, the average mass of the isotopes. The average mass of isotope of an element when compared to 1/12 of carbon-12 isotope. Okay? When compared to carbon-12, 1/12 of the mass of carbon-12. So you must know how to define relative atomic mass. Now, how to calculate it also, you know, we have, let's say, chlorine. We have chlorine 35. Our tutorial has already explained this, but I'm just throwing a little bit of light. Chlorine 35, and we have chlorine 37. We don't just say, oh, why don't we just say, sorry, I have to write chlorine. We don't just say, oh, since this is 37 and 35, why don't we just say 37 plus 35 divided by 2, and then we get 36. No, but that's not the way. We have to look at the percentage of abundance. Percentage of abundance. This one is 3 times in occurrence than this one 1 time. So meaning we have this one 3 times. 3 times of chlorine 35 as to 1 times a percentage abundance of chlorine 31, which means 75% to 25%. This one occurs only once. So you can either use a percentage to calculate. This is chlorine 35. Okay, so even if I don't put the atomic number, you already know it's 17. Okay, so 17, even if we don't put it, you already know it's for chlorine 17, the atomic number. Okay, we're talking about the mass, because relative atomic mass, we are calculating the mass, the average mass of the isotope, because this is an isotope, right? So we look at their percentage of abundance. We don't just say because we are calculating the average mass, we don't consider the percentage of the abundance. We have to look at the percentage of the abundance. So this one is available 3 times, like ratio 3 to 1. Ratio 3 to 1. Okay, so we can add this plus this plus this, then plus this, all divide by 4. We get the average masses. So you can do it in this way, but the way that I prefer is to find the percentage of abundance. So this plus this, we get 70 plus another 35, we get 105, right? We get 105, right? 105 plus 37. 105 plus 37, what do we get? So we do this if we want to find the average mass. Because we must look at their percentage of abundance, because they have ratio. Divide by 4, we'll get 35.5. So it's either you do it like this to get the relative atomic mass. Okay, remember relative atomic mass is the average mass of isotope of an element when you compare to carbon-12 isotope. 1/12 of the mass of carbon-12 isotope. Okay, so we get 35.5, right? So another way to do it that I feel it's more unique, it's the percentage of abundance. Since this occurred 3 times, this occurred 1 time, this will be 75%. So I'll say 35 times 75 over 100. Since it's 75%, I do 75 over 100. For this one, I can put it in a bracket for my chloride 35 plus, we say chloride 37, we say 37 times 25%. This one, the percentage of abundance is 25. They can give it in a graph. You can read the value from the graph, 25%, or they give it as percentage over 100. You group this one. So you see when you solve these two, you get, eventually you get 35.5. Key this in your calculator, you get 35.5 as your relative atomic mass. So our AR is 35.5. You need to know how to do this, okay, if you want to progress in this subject called chemistry. Okay, you need to know how to do this. So our relative atomic mass is 35.5 in this regard. So this is all I want you to know in this place, and then we move on. For every other one is so with this we've come to the end of chapter 2. Thank you for joining us.